In the sciences, we celebrate big ideas. We celebrate the people who see patterns the rest of us miss. But we rarely celebrate something more fundamental, the whole human mind that carries those ideas, with its strengths and its storms. Today, I'm going to talk about one of the brightest lights of 19th century physics, a person who shouldered the weight of both scientific opposition and personal suffering, Ludwig Boltzmann.
We'll be right back after a quick word from my advertisers.
Today, I'm going to normalize a conversation that too often sits in the shadows of our labs and lecture halls: mental health and science. Imagine Vienna in the 1870s. A young Ludwig Boltzmann sits at his desk, surrounded by chalk-stained papers, wrestling with a question that has haunted physics for decades. Why does heat always spread out? James Clerk Maxwell had shown that the velocities of gas molecules follow a statistical pattern, but Boltzmann couldn't let it rest there. He wondered, could this same logic apply not just to gases, but also to liquids, and even the vibrating atoms inside a crystal? Night after night, he calculated. He sketched particles, colliding, scattering, and vibrating. And then the insight hit him. Not as a bolt from nowhere, but as the culmination of years of struggle. Disorder increases, not because nature wants it to, but because there are simply more ways for particles to be spread out than bunched together. Dispersion, he realized, was not mysterious at all. It was mathematics. It was probability. And in that moment, he penned the relation that still sits at the foundation of modern physics. S equals K times the logarithm of W, which is entropy equals a constant that is multiplied times the logarithm of the number of microscopic states that make up a macroscopic reality. Basically showing that if there are more ways to be disordered than ordered, then disorder wins. It was brilliant. It was a unifying vision. Gases, liquids, solids, they all obeyed the same statistical law. Thermodynamics was no longer an island apart from mechanics. Boltzmann had shown that the chaotic dance of countless molecules, when viewed statistically, produces the smooth, one-way drift toward equilibrium that we experience in everyday life, like when coffee cools and smoke spreads and heat flows. What feels like the arrow of time emerges not from a hidden force, but from the overwhelming probability that disorder will increase. But his triumph didn't come without a cost. Many of his contemporaries rejected the very idea that atoms were real. To them, Boltzmann's equations were abstract fantasies. He was mocked, criticized, and even dismissed. As he clung to the conviction that the arrow of time could be explained by mathematics, his self-esteem and view of his self-worth began to crumble. It soon began to destroy him emotionally. And Boltzmann's despair wasn't unique to his time. The pressure to perform, the sting of rejection, and the loneliness of carrying ideas that others refuse to believe, these are still with us. Today, scientists and students across academia face similar struggles. They take the shape of anxiety, depression, burnout, and sometimes even suicide. And the numbers tell us just how heavy the burden has become. The academic world, from students to tenured faculty, is grappling with a serious mental health crisis. Roughly 37% of academics experience anxiety or depression, compared to only 19% in the general population. Among students, the figures are particularly alarming. Up to 44% report depressive symptoms, 36 to 41% endure anxiety, and 14% contemplate suicide, with self-harm incidences found in nearly 3 in 10 students. PhD candidates fare no better. Almost 1 in 4 suffer from clinical depression, and 1 in 6 face anxiety. Suicide attempts further underscore the severity. Approximately 24,000 occur each year among college students, making it the second leading cause of death on campuses. These statistics reflect the devastating impact of poor work-life balance in academia. where relentless pressures, insufficient support, and blurred boundaries between professional and personal life contribute to mounting psychological distress. Academia's mental health crisis is being driven by overlapping pressures that are measurable in the data. The culture of overwork is intense. 3 out of 4 graduate students report working for more than 40 hours a week, and 1 in 4 exceeds 60 hours. Faculty often log over 50 hours themselves, with the mindset of publish or perish looming over every career stage. Job insecurity compounds the stress. Nearly 70% of university instructors in the United States are now off the tenure track, and half are part-time with median adjunct pay only about $3,900 per course. A quarter of adjuncts live below the poverty line. Just let that sink in for a second. Adjuncts. These are people who devote their lives to educating students, and yet they are treated so poorly that they barely have enough money to survive. And it would take one healthcare crisis, just one, to force them into a situation where they are unhoused. This is heartbreaking. And then for students, financial strain is relentless. Average loan debt hovers near $39,000 per semester. Tuition has more than doubled in real terms since the 1990s. And 59% report food or housing insecurity, with 14% of students experiencing homelessness. Even stipends for graduate students often fall short. In physics, about 70% of first-year students earn below the local living wage. Social isolation adds yet another layer, with roughly 1 in 4 PH students reporting severe loneliness, which correlates strongly with burnout and depression. Meanwhile, access to mental health care lags behind the need for mental health care. More than a third of students screen positive for depression or anxiety. Nearly 40% never receive therapy or medication, often due to cost, time, and long waits. For marginalized groups, yeah, you guessed it, the risks are even higher. 1 in 5 students entering counseling reports recent discrimination, which is directly tied to elevated distress and suicidal thoughts. And the pandemic's aftershocks intensified everything, driving anxiety and depression rates among students up more than 12 percent points in just 5 years. Together, these pressures explain why depression, anxiety, and suicidal ideation are not isolated experiences, but systemic outcomes of academic life today. These are not side notes to science. This is the culture in which science happens. So today, as we visit Boltzmann's battles over atoms and entropy, I'm also going to talk about bipolar disorder and explain what treatments like cognitive behavioral therapy, along with access to medication, actually do and how they really do help, and why mental health care is so necessary in academia. So, who was Ludwig Boltzmann? Well, Ludwig Eduard Boltzmann was born in Vienna in 1844. He trained at the University of Vienna, and by his mid-20s, he was a full professor. From the very start, he cared about a question that sounds simple and turns out to be profound. How do the motions of unimaginably small particles give rise to the warm, smooth behavior we see at the human scale? Temperature, pressure, friction, heat flow. Well, the bridge he built between the microscopic and the macroscopic is what we now call statistical mechanics. When Boltzmann earned his doctorate in Vienna in 1866, he was barely 22. His mentor, Joseph Stephan, introduced him to the revolutionary ideas of James Clerk Maxwell, and young Boltzmann was instantly captivated by the hidden dance of molecules. He was restless, brilliant, and determined to push Maxwell's kinetic theory further than anyone had imagined. His first professorial job was in Graz, The university halls echoed with chalkboards scrawled full of collisions and equations, while outside, Europe's scientific community buzzed with debates about the nature of heat. He spent seasons abroad, working with the likes of Bunsen, Kirchhoff, and Helmholtz, sharpening his tools and testing his ideas. Each city, Graz, Munich, Leipzig, Vienna, became another stage for his restless energy. Then, in 1872, he made his first great leap. Boltzmann wrote down what is now called the Boltzmann equation, a description of how the velocities of particles in a gas evolve as they strike and scatter off one another. It was bold, it was new, and from it, he carved the H theorem, a mathematical proof that gases do not linger in disorder forever, but overwhelmingly drift toward equilibrium. This H theorem suggested that the second law of thermodynamics, the law that says heat flows from hot to cold, that entropy always increases, was not just a mysterious principle of nature. It was the inevitable outcome of statistics, the law of large numbers written in the language of atoms. But with the ambition came the headwinds. The second half of the 19th century was not universally friendly to atom talk. Some of the most influential voices in European science either doubted or openly rejected the reality of atoms. The chemist Wilhelm Ostwald, a towering figure in physical chemistry, promoted an alternative program he often called energetics, which aimed to explain nature solely in terms of energy transformations without commitments about microscopic particles. The philosopher and physicist Ernst Mach was skeptical of unobservable entities in general and of atmospheric pictures in particular. Boltzmann found himself not only doing hard physics, but defending the very idea that microscopic particles existed. It was more than a style of difference. If you say that entropy goes up because systems move to more probable configurations, then probability must have a meaning. If you say gases have pressure because molecules ricochet off the walls, you must accept molecules. Boltzmann did both, and he did it loudly, publicly, and bravely. But not everyone agreed that his H theorem showed what he said it did. A former mentor, Joseph Lockschmidt, raised the reversibility objection. If microscopic laws are reversible, how can macroscopic behavior be irreversible? Later, Ernst Zermelo, drawing on Poincaré's recurrence insight, argued that systems should eventually return close to their initial states. These were not petty criticisms. They were deep challenges that pushed Boltzmann to emphasize the statistical character of his reasoning. In response, he clarified that the march toward equilibrium is overwhelmingly likely, not metaphysically guaranteed. The universe does not break its laws, it plays the odds.
We'll be right back after a quick word from my advertisers.
Meanwhile, while he was doing all of this, the human story was unfolding. Boltzmann was gregarious in lectures and could be wonderfully funny, yet he was also very sensitive to criticism and subject to bouts of depression that worsened when work turned combative. He moved between posts, he struggled physically with poor eyesight and asthma, he poured his life into a view of nature that many of his contemporaries called speculative. Vienna, the late 1870s. The air in the seminar room was thick with smoke and chalk dust. Boltzmann had just finished lecturing on his H theorem when a voice rose from the back. Johann Loschmidt, calm but pointed, asked why entropy must always increase. If every molecule's motion could be reversed, he argued, then Newton's law demanded that order should rise again. Did this not undo Boltzmann's law? Boltzmann leaned forward, animated. Yes, in principle, he conceded, the reversal could happen. But think of the odds. The probability was so vanishingly small that in practice it never would. Entropy's rise was not impossible to escape. It was simply inevitable by numbers. The arrow of time, he insisted, was born of probability. The room stirred with debate. Years later, in Berlin, the challenge returned to a new form. Ernst Zermelo stood armed with Poincaré's recurrence theorem. No matter how vast the system, Zermelo argued, given enough time, the molecules must eventually return to their original state. Entropy could not march forward forever. Boltzmann's response was passionate but weary. Recurrence was mathematically certain, yes, but the timescales were longer than the age of the stars, longer than the universe itself. For all practical purposes, the coffee would never heat itself. The smoke would never gather back into the match. Equilibrium remained the destiny of matter. But the harshest blows came not only from paradoxes, but from philosophy. In Vienna, Ernst Mach raised his hand and dismissed atoms altogether. They were metaphysics, he said. Energy was real. Molecules were mere speculation. Boltzmann bristled. His voice tightened. Molecules were no metaphysics, he insisted. They explained the second law. They gave substance to kinetic theory. They made sense of heat. Dismiss them if you must, but one day experiments would reveal their fingerprints beyond doubt. The audience murmured, unconvinced. Boltzmann looked around, convinced himself, but increasingly isolated. By the 1890s, the weight of skepticism was heavy. His hair had turned gray, his study cluttered with letters, some supportive, many were critical. He read them aloud bitterly. They say atoms are figments that probably has no place in nature. After all these years, am I just talking to myself? He sighed, pressing his hands into his face. And yet, in Leipzig, around 1900, among his students, Boltzmann's spark returned. His booming lectures lit up the chalkboard. "Do not fear probability," he cried, the chalk striking emphatically. "Embrace it. The laws of thermodynamics flow from the countless possible states of molecules. Entropy is not a curse. It is the mathematics of time itself." His students leaned forward, laughing at his jokes, sensing the scale of his vision. They adored him. For a moment, he was invigorated. Still, whispers of doubt lingered at the edges. He pressed his insight into other problems too. He argued publicly against the energetics program, insisting that energy without particles is a reshuffling of words, not an explanation. He taught courses in natural philosophy. He mentored, he argued, he laughed, and at times he despaired. He watched as critics with enormous influence doubt the microscopic world he considered essential. He kept going. His story faded into silence, leaving behind the lingering question of what brilliance costs and what it means when a mind is left alone to fight it. It is tempting to quarantine the struggles of the past inside sepia photographs. It is tempting to believe that the pressures that weighed on Boltzmann evaporated with time. But talk to scientists today and you hear a different story. Long hours, insecurity, a feeling that asking for help is a liability, not a strength. We talk a lot about brilliance in academia, about ideas, discoveries, and breakthroughs. But brilliance needs fuel, and it can burn out fast if we don't take care of the mind behind the work. Exhaustion, anxiety, depression, even bipolar disorder, or even schizophrenia. These are not rare in universities. They are common human realities. And while no podcast can replace professional care, there are tools, both psychiatric and psychological and practical, that can help. And one of the most studied methods is cognitive behavioral therapy, or CBT. At its heart, CBT is about noticing the stories we tell ourselves, like, "I'll never finish this paper," or "I don't belong here," or "I don't deserve this high grade," or "I am a failure." We hear these things we tell ourselves, and it's important to gently test these thoughts. Many of us fall into common traps, catastrophizing, assuming the worst, black and white thinking, where we label ourselves as total failures for a single mistake, or mind reading, where we convince ourselves that everyone around us is judging us. CBT invites us to challenge those patterns. If we catch ourselves thinking, "This presentation is going to be a disaster," we can ask, what evidence do we actually have? Has every talk we've ever given been a disaster? Usually, the answer is no. Reframe that. Reframe that with, I may feel nervous, but I've prepared before and I can do it again. It is like retraining a restless horse. The thoughts will still buck and pull, but with practice and steady stirrups, we can guide them in a healthier direction. There are also behavioral techniques, setting realistic goals, breaking tasks into smaller steps, and rewarding progress rather than seeking perfection. A simple list of 3 achievable tasks for the day can feel more powerful than a crushing to-do list that never ends. I feel that one. Lifestyle changes matter too. Predictable routines, waking, working, and resting at regular times can stabilize mood and energy, especially for those managing bipolar disorder and even schizophrenia. Movement and exercise act like natural antidepressants, improving focus and sleep. Even a 10-minute walk between classes or lab sessions can make a difference. Sleep hygiene is another cornerstone, keeping devices away from the bed, winding down with calming cues like a dim light or reading, and aiming for consistency. And finally, connection. Isolation magnifies struggle, while community lightens it. Talking with your peers, joining support groups, or simply admitting to a friend, hey, I'm having a hard week. That can turn the weight of silence into shared strength. Resilience isn't about toughing it out alone. It's about building a network of people who remind us that we are not defined by our hardest days. Academia may glorify long hours and endless output, but the real foundation of discovery is well-being. Protecting your mind is not separate from the work of science and scholarship. It is the work. If you or someone you know is struggling in the United States, you can always call or text 988 to connect with the Suicide and Crisis Lifeline. Hopefully that will never go away. Outside of the United States, the International Association for Suicide Prevention, IASP, maintains a global directory of crisis centers at iasp.info/crisis-centers-helplines. And I'm going to put that link in the show notes and in the blog. And if you are in immediate danger, please call your local emergency number and know deep within your heart that you are loved and you are wanted in the world and that you are surrounded by people who genuinely love you and care about you. It may not feel like it, but it's true. There are people in the world who love you and care about you. And I don't even know you. I don't know who's listening to this, but if you're out there and you are struggling in academia or even in your job as you're driving into work and you're feeling the weight of the world, know that I don't know you, but I love you and I appreciate you. And I appreciate you being part of this world of knowledge and curiosity. Know that you are loved.
We'll be right back after a quick word from my advertisers.
It wasn't until 33 years later when Albert Einstein published a theory of Brownian motion that showed that subtle fluctuations and measurable diffusion could be explained if molecules were real and numerous. Boltzmann's theories were validated. Within a few years after Einstein's theory on Brownian motion, the experimentalist Jean Perrin carried out careful experiments testing Einstein's predictions. By tracking microscopic particles under a microscope, he was able to measure their displacement statistically and thus calculate Avogadro's number with remarkable accuracy. His results were published in a 1909 paper, and they confirmed the molecular kinetic theory of heat. The atom was no longer convenient fiction. It was palpable in the statistics of wandering specks. Both of these brilliant minds validated Boltzmann's theories. Tragically, Boltzmann did not live to see that vindication fully accepted. When Einstein's 1905 work on Brownian motion appeared, Boltzmann's defenders could finally point to an effect that was both visible under a microscope and calculable on paper. Jean Perrin's measurements in the years that followed cemented that connection. The world of atoms and molecules did not merely tidy up the equations. It left Boltzmann's fingerprints in a jittering, dusty light. We cannot know how Boltzmann would have felt to see that vindication turn into consensus. We can say that his work now carries the weight of an entire century of physics. His equation threads through statistical mechanics, quantum theory, cosmology, and information theory. His legacy is etched into the very language of physics, a single lowercase k, the Boltzmann constant, quietly carrying his name as it links temperature to energy. And his legacy raises a moral we should not ignore. Ideas do not walk into the world alone. People carry them. So let's return to 1906, when Boltzmann was struggling under the weight of his emotions. Boltzmann was worn down, his eyesight failing, his health fragile, his spirit battered by decades of rejection. The debates with Mach and Ostwald had left deep scars, and though new experiments were beginning to confirm the atomic world he fought for, he would never live to see his ideas fully vindicated. In September of that year, at a seaside retreat in Duino, Italy, Ludwig Boltzmann ended his own life. His students, his colleagues, his family, all were left to reckon with the loss of a mind that stretched physics into new realms. It's easy to turn Boltzmann into a statue and place him under a glass dome, the great scientist who had an equation engraved on his tombstone. But a more honest telling is humbler and more useful. He was a person who found a way to make sense of the world's order and disorder by counting possibilities. He was a teacher who defended a picture of nature that many people called metaphysics. He was a colleague who felt the sting of public criticism. He was a father and a husband. He struggled. Today, his equation is carved on his gravestone in Vienna, and it remains one of the most profound insights in science, that the universe does not run on destiny, but on probability. We do not honor him by romanticizing his pain. We honor him by learning from him. We honor him by building research environments where bright minds can do bright work without pretending to be invulnerable. We honor him by listening when a colleague says, "I am not okay," and by welcoming, not punishing, that honesty. We honor him by recognizing that routine is medicine, sleep is medicine, therapy is medicine, community is medicine, work-life balance is medicine. We honor him by remembering that probability, the mathematics of what is likely, applies to culture too. If we increase the number of supportive configurations of academic life, we make it overwhelmingly likely that more people will thrive. If today's conversation stirred something in you, here are 3 ways forward. First, share this episode with a friend. Normalize conversations about mental health the way we normalize lab meetings and preprints. Second, if you are in academia, help nudge your lab or department toward healthier defaults, predictable schedules, clear boundaries, kind feedback, and explicit encouragement to seek help when needed. If you lead a group or if you are a professor, please put resources in your syllabus and onboarding packets so that support is built into the culture, not left to chance. Please do this for the next generation of academics. Third, if you are struggling, please reach out. In the United States, you can call or text 988 to connect with the Suicide and Crisis Lifeline. Outside the United States, the International Association for Suicide Prevention has a global directory of resources. You can find that at iasp.info. And if you are in immediate danger, please call your local emergency number. Because science only advances when people do. History may not remember every equation, but it will remember whether we built environments where minds could thrive. Boltzmann's story reminds us how fragile even the greatest among us can be. And so I'm going to leave you with words I return to often. Resilience is not about going at it alone. Resilience is a group activity. Resilience is about being there for each other. That is how we grow as a healthy society. And I believe all of those words with all of my heart. And I hope you do too. Until next time, carpe diem. Thank you for tuning in to Math Science History. If you enjoyed today's episode, please leave a quick rating and review. They really help the podcast. You can find our transcripts at mathsciencehistory.com. And while you're there, remember to click on that coffee button because every dollar you donate supports a portion of our production costs and keeps our educational website free. Again, thank you for tuning in. And until next time, carpe diem.